Uh, Hello, I'm Ji Young, and today I'll be presenting about this paper. It's called Expressibility and Entangling Capability of Parameterized Quantum Circuits for Hybrid Quantum Classical Algorithms. And I believe this was published in 2019. And yeah. So here's the motivation. So there's a class of quantum algorithms called variational quantum algorithms or hybrid quantum classical algorithms. And these algorithms try to use NISQ hardware where we use the quantum hardware to calculate some loss function value, and then we use the classical optimizer to optimize the loss function by changing some parameters in the quantum hardware. And this is usually in the form of parameterized quantum circuits or PQCs. So we have some free variables that we can change, which are usually just the rotation angles of various quantum gates. Now the problem is we can actually map many different problems into variational quantum algorithms, but how can we describe the characteristics of a PQC, and how can we use this to design a good PQC is a very important problem when we're trying to actually run these quantum algorithms. So this paper tries to deal with these problems by proposing two descriptors of PQCs. So basically, we first need to answer what do we want from PQCs, and also how can we quantify these characteristics. Now, the first attempt is something called expressibility. So the question is, let's say that we want the PQC to produce states that well represents the Hilbert space. So it doesn't just create a certain state or some states like very random, very sparsely distributed. We want the PQC to produce states that is very evenly distributed over the Hilbert space, and we want to be able to quantify this this characteristic. And so in order to do that, we first consider a deviation from a state T design. So we have two terms here. The first one is basically just all of the quantum states in some sort of like a mixed state, except that the integration is over the Haar random measure. And on the right-hand side, we have another term, but in this case, these states are not sampled from the Haar random measure, but it's sampled from the PQC. So we can expect that if the PQC creates exactly the same as the Haar random measure, then this will equal to 0. But normally this will not be equal to 0. And we call this the deviation, or A. And let's say that we want to know the norm of this A. So normally we would want this to be small. And if we calculate the norm, we get this value. Here, this mu t is simply the second term. And from this, we can see that actually the terms is related with something called frame potentials. And frame potential is defined as follows. And for the Haar random measure, actually it's written as follows, where dt sim is some dimension of the some symmetric bases. But anyway, so if we look at the HS norm of A, we can see that actually it is equal to just the the frame potential of the states, ensemble of states created by the PQC, and the difference between that and the ones created by the Haar random measure. And since this is a norm, this is larger than or equal to 0. So we can see that actually the minimum of the PQC frame potential of the PQC will be the frame potential of the Haar random measure. And actually, this is a stronger version of this is proven where the first T frame potential, so T is some integer value, it could be 1, 2, 3, 4, so on and so forth. The first T frame potentials achieve their minimum if and only if the ensemble is a state T design. So if another thing to note is that the state T design by definition as if we have some ensemble of states, and if it is a state T design, then if that T value gets higher and higher, we can say that the ensemble of states more well represents the Hart random states. So if Hart random measure. So if we have it equal for 2, then it's called the 2 design, and so on and so forth. So basically, we want the distribution of this value to be very similar to the Hart random measure. And so that's where we get the idea for this expressibility measure. So it is, since we have some fidelity with the probability, we want this probability distribution of the fidelity caused by the PQC to be the same as the probability distribution of the fidelity caused by the Hart random measure. So a natural way to write that is just some distance between two probability distributions. So one natural way is to use the KL divergence. And so this paper suggests using this value as the expressibility. So one thing that can be a problem here is how can we actually use this in practice? Because it would be very difficult to calculate this probability distribution for a given PQC. And so this paper suggests rather than actually calculating this probability distribution, that we can actually just sample random states from the PQC, and then we can calculate the fidelity between those states. And then just through that, we can estimate the probability distribution by just creating a histogram. And then we can find the KR divergence of that histogram and the histogram caused by the Hart random measure. And actually this distribution is known theoretically. So we can easily do that. And an example is shown here. So there are four circuits considered here. So the ideal circuit is just the identity. And so this has low expressibility, right? It just gives the same outcome as the income. So if we have a fixed input state, then this will not be similar to the Hart random measure. And so we can see B is just the plot of all the sampled states when using that is used for the calculation. And as we go to the right, we can see that the states are more well distributed around this clock sphere. And so when we reach this arbitrary unitary, this is actually exactly the same as the Hart random measure. And so in this case, we can see that the KL divergence is very small. While for the ideal circuit, this is not so it has actually the maximum KL divergence for this setting. And you can see the relationship between expressibility and the frame potentials in the bottom graph. So the y-axis is the frame potential, and then the moment or the t value of the frame potential is shown on the x-axis. And actually, I don't know if you can see it, but the Walsh bound or the minimum bound is shown on the bottom. So if the values are very close to this bound, then we can say that it is very close to the Hart random measure. And so for the ideal circuit, it is very far from the minimum. And as we go from circuit A, B, and uniformly sampled, we can see that actually the frame potential values become closer to the minimum bound. Are there any questions so far? So it's like, so I guess there will be some rigorous mathematical definition, but sorry, I didn't memorize that one. But basically, it's like some uniform distribution over all unitaries. So we can use it like some probability distribution over all unitaries. So we can think of some situations where we want to integrate over unitaries, right? So in that case, we usually use Hart random measure. Are there any other questions?
So in the diagram, what exactly is the arbitrary unitary? So how does that circuit would look like? It's decomposed.
I guess we can just decompose any single qubit unitary into, like RZ, RX, and R1, right? And then so yeah, that's basically. So actually, so for one qubit, it's kind of easy to think about the Hart random measure personally, but because it actually we can directly correlate it with the arbitrary single qubit rotation, which has just 3 variables, right? But it's kind of difficult for personally for me for like higher dimensional hybrids. But anyway. Okay, so this is one method that the paper chooses to talk about some description of the PQC. And the next one is really short. It's called the entanglement capability. So we know that entangled states and creating entanglement is very important in quantum computing. And it's one of the big things that sets quantum computing apart from classical computing. So we can think of entanglement as a very important resource. And so it's natural to think about, to want a PQC that creates entanglement. And so so this paper wanted to create some description of a PQC that encapsulates how well this PQC creates entanglement. And so naturally they use some entanglement measure. They chose this Meyer-Wallach entanglement measure because it's easy to compute, and the properties is what's important here. So it's invariant under local unitaries, and its value is between 0 and 1. And also it's equal to 0 if and only if the input state is a product state. So this actually this entanglement measure, I believe, only works for pure states. And so the entanglement capability is simply just the average of the entanglement measure value for all states, for states sampled from the PQC. Maybe I can actually show an example of how this works. Can you see this slide? So let's say that we want to calculate the this Meyer-Wallach entanglement measure of a Bell state. And in order to do that, we can see we need to calculate this value, and I will only calculate this one. Actually, it's easy to show that this is the same as this one. So I'll just calculate this one. We first need to know what this is. And here, B is either 0 or 1. J is the number of the qubit, index of the qubit, and this caret means that it doesn't exist. So basically the output is either 0, or basically nothing, or the original state with the index gone. So in this case, we want to know here. And so for this case, we want to look at the first qubit, and if it's exactly the same, if it's 0, then it's erased and the rest remains. And for this case, it's not 0, so this delta function becomes 0, and so we don't have any state. So this result in this one, you can see that it's not trace preserving, but anyway, we can do the same thing here. And in this case, we have the first qubit is not 1 for this basis, so this is erased. And the first qubit is 1 for this basis, and so the first qubit is erased, and the second qubit remains. So we have this, and now we need to find this generalized distance between these two, and that's simply just and if we just follow the expression there, this should equal to 1/4, I think. Yeah. So in this case, we have 2/4 times 1/4 plus 1/4. It's equal to 1. Yeah. So for this maximum entangled state, we have 1. Anyway, so the most important thing is that they have some entanglement measure, which follows these properties, and they just simply calculate this entanglement measure for all sample states. And they did lots of numerical experiments that basically tested these two descriptors for many different types of PQCs. And they used 19 different 4-qubit PQCs, and this is all shown here. So basically, they just use all of them, and then they calculated the entanglement capability and the expressibility. And now let's look at the results. Okay, so the x-axis is the circuit ID, and the y-axis is expressibility. And since expressibility is the distance, we want this to be small, right? So low expressibility is equal to high KL divergence, and actually low KL divergence is equal to high expressibility. And they also tested changing the number of layers. So we can actually just repeat the same circuit over and over again, but of course using different parameter values. And that's one way of toying with the expressibility. And we can think that actually adding more layers will improve the expressibility. And for most cases, it was true. But as you can see in the circuit 13 case, that usually the expressibility is saturated at some point. So in this case, if we have like 6, 7, or 8 layers, it wouldn't make much of a difference. It would only just increase the cost of the circuit. And the next is the entanglement capability results. Likewise, the circuit ID is shown in the x-axis, and for the y-axis, we have the entanglement capability. And likewise, they change the number of layers, and the results are as follows. So on one extreme, we have circuit 1, which is just, sorry for the bad resolution of the image, but it's just local unitary, so this would not create any entanglement, and therefore the entanglement capability is 0, even if we increase the number of layers. And on the other hand, on the other extreme, we have circuit number 9, which was very good at creating entanglement. But one thing that they noticed is that a good expressibility usually meant good entanglement capability, but the converse was not true. So circuit 9 is very good for entanglement capability, but if we look here, circuit 9 is way over here. So it has bad expressibility. And they also compared the difference between 2 qubit gates. So basically, they had the same exact architecture, except that they just changed the type of 2 qubit gate. So for the circuits on the left-hand side, we have the 2 qubit gates as control rotation Z. And on the right-hand side, we have the 2 qubit gates as control rotation X. And the rest of the circuit is exactly the same. And in this case, we actually saw that CRX was better than CRZ. But honestly, I'm kind of skeptical on this result because I think it would depend very highly on the rest of the circuits. And sometimes maybe there can be some cases where because maybe these gates commute with each other and they can cancel out or be redundant or something. So actually, I'm not really sure about how useful this result is, but this is one analysis that they did. And another one is they compared the 2-qubit gate configurations. So they kept the single qubit gate configuration the same, but they changed how we act 2-qubit gates with each other. So they tested 3 configurations. The first one is nearest neighbor, so we just connect the neighbors. Then the other one is circuit block. So we do connect the layers, but we also include this last one, which is just basically creates a ring. And then we have all-to-all. So basically, we connect every single qubit with each other. And we saw that the expressibility and entanglement capability is the best for all-to-all, but actually it's very similar for circuit block. And since all-to-all is very costly in terms of quantum resources, such as depth or connectivity, we can see that circuit block can be a very good alternative. And so in conclusion, this paper introduced these two values for PQCs. So they provided some ways that we can analyze PQCs in a meta way. And expressibility saturated as number of layers increased. And good expressibility usually meant good entanglement capability, but not vice versa. And actually, there's more analysis in the paper, especially in the supplementary material. They have some discussion about relation with quantum resources and etc. So if you're curious, you can read more about it in the paper. And one downside is actually recently I was calculating expressibility of some circuits, and I found that it's actually it can be difficult to calculate expressibility for a high number of qubits because the hard random probability distribution for the fidelity, it becomes very one-sided. So it's so the probability to get like a very high fidelity for a high qubit hard random measure is very low, which can be expected because of the dimensions increase. And in that case, it's very difficult to calculate the KR divergence between the fidelities calculated from my PQC and the hard random measure. So I found that actually it's very difficult to calculate in that case, and maybe there needs to be some better way to calculate expressibility for large number of qubits. Thank you.
Can I ask a question?
Yeah.
So it seems that in the paper they will be considered equals 1.
That's a good question. Yeah.
So maybe mention about them or
Sorry.
is there like a difference between fidelity?
Yeah. So, like you said, maybe it was a problem with my explanation, but we can see that so FT is defined like this, right? But actually, we can see that this is just the teeth moment of the fidelity, right? And the KR divergence looks at the distance between two probability distributions. So it would consider all of the moments, right? It would consider all of the moments of the probability distribution, right? It would compare all of the moments of the probability distribution. So no, yeah. So the KR divergence is it compares two probability distributions, right? And the moments of the probability distribution is one characteristic, are the characteristics of the probability distribution, right? So if we compare two probability distribution using KR divergence, then effectively we're looking at all of the moments, right? So that's why it looks like it only looks at t equals 1 because we're only considering the fidelity, but in fact we're considering all of the moments, so we're considering higher t.
And at the last slide, you mentioned that a good expressibility is to good entanglement capacity, but not vice versa.
Right.
So that means the circuit with good entanglement capacity can be bad, have a bad expressibility.
Right. So that was actually just shown like in a numerically, like in a numerical experiment. You can see the circuit 9 over here. This has good entanglement capability, right? But if we look at expressibility, it's bad.
But the growth of expressibility is very rapid in the circuit.
Right, that is true. So, but actually, one interesting thing is that for circuit 9, actually, the entanglement capability decreases with the number of layers. Actually, they talk about more about this detail in the paper, but they suggest that actually it will oscillate and it will eventually converge at this this black line. Oh, sorry, I didn't explain what this black line is. This black line is the entanglement capability, theoretical entanglement capability of a Haar random measure. So yeah, so they suggested that eventually it will oscillate and converge to this value. But anyway, for this case, for circuit 9, actually it decreases the entanglement capability. And I think that as long as we have some good example, some good counterexample, we can argue that this is the case, right? So this means that it's not necessarily the case that good entanglement capability equals good expressibility, which we just need some good counterexample. So circuit 9 is a good counterexample.
You're going to train something that could be or something 9 or depends on how you can get that to so
I mean, I guess it's always a trade-off between those two things, right? Trainability and expressibility. So I think it would be very problem specific, and yeah, you should try, I think. Yeah, I think that's a very good point. And one of the downfalls of this type of research is that eventually, when we try to actually use these ansatses for our purposes, we will need to just do trial and error. Like this is a good way to get a vague idea of what these PQC do, but eventually it will be problem specific. Yeah.
Is there any like open source tool to calculate the expressibility and entanglement capability?
I'm not sure if there's something open source, but it's actually really easy to code. So.
And the other question is, like most of the time when circuit has a more higher expressibility, kind of treat it as something useful, right?
Right.
But like if we consider it this way, like if we have a problem and there is a target space, and like if we have a more expressible circuit, might not be a useful thing, right? To have a more expressive. So is there any like this kind of matrix maybe, for example, if we have two circuits with same expressibility, but if our like problem is one has like a smaller solution space and the other has just a bigger one, we try to compare the usefulness of those two circuits. The one with higher expressibility and larger solution spaces can be useful, right? So like I'm kind of curious, there is this dynamic to measure for problems maybe usefulness.
Actually, that's one of the points in the discussion of this paper. Like they talked about like you said, like depending on the problem, we don't always need for the PQC to be able to express every single state in the hyperspace, right? And actually, it can be a bad thing for trainability or like having a very strong and useful inductive bias is always good in a machine learning model, right? So in that sense, then sometimes we don't need very high expressibility. So like you said, that can be one that can be one way of one method of research, and actually they do discuss that it is that they need to do something about that. But I'm not sure if there's anything like that.
Like there's no any specified metric.
Not to my knowledge, but there can be something. Yeah.
Very possible presentation. PPT uses it from key design.
Oh yeah.
What is actually
Okay. So hopefully I don't mess this up, but the so like a set of unitaries can be a unitary T design. And we can also talk about state T designs, but first I'll talk about unitary T designs. And I believe a unitary T design is when so let's say that we have some polynomial of order t, and it's t comma t because it can be in order of t of w and also of w dagger. But anyway, let's say that we have some polynomial here, and we want to integrate this over the Haar random measure, and this UI, this set UI is unitary T design if this this integration over the Haar random measure can be written as just the average over this set. So yeah, so you can see that this is just the polynomial with the input as the UI, and we can just take the average. And if this is equal to just actually the integral over the Haar random measure, then this is called a unitary T design. And we can derive a state T design easily from this. So so if this is a unitary T design, then for any states, then this is a state T design. I believe this is a state T design. And yeah, from like characteristics of the Haar probability Haar measure, we get some characteristics about this unitary T design. Yeah, but I always look these things up when I need it, so I don't memorize everything. But yeah, so actually from this we can calculate. There's some ways of calculating these types of things when we know like which design it is. And so it's actually useful to, prove certain stuff. Like for example, I know Xion and I also looked at the Barron plateau problem. So we can, we can actually calculate the Barron plateau phenomenon using these types of characteristics.
So maybe this is a little off the topic of this presentation. So I'm just curious, like when you begin to solve a problem using like a PQC, so how do you decide like which ansatz do you start with? Like how do you know like which ansatz would be appropriate for a certain problem?
That's a good question, I think. Sometimes the problem itself has some characteristics. I know that you all studies VQE, and in VQE, often depending on the problem Hamiltonian or depending on some symmetries of the system, we know that the states should follow some rules. And so we can design something, an ansatz like that. Or one example is actually the topic of my thesis, actually. So maybe I can talk about that. So let's say that we want to deal with some graph data. So we have some graph. But the problem with this graph is that it doesn't really matter which node, what we name the nodes. So actually all like classical machine learning methods also have some invariance about the permutation of these nodes. And we still want that for quantum models, right? So one way to do that is to designate each node a qubit. And then the way that we operate on this is we can apply some single node of operation and then operation along the edges. But the thing is that these must be all the same. And that these should commute. In that case, then it doesn't really matter which order we put these nodes. If we use this type of mapping, then even if we have this type of permutation, then the resulting state, actually in that case, it's not invariant, it's called equivariance. But anyway, it would follow the symmetry that we want. So in those cases, then we can have some idea of the form that our ansatz can be. But otherwise, if there's no such structure, then I guess it's just trial and error.
And also, so for your thesis, do you like manually assign the qubits like according to the graph that you want to like encode? Like, so what I'm saying is that when you have like those 3 qubits, do you actually look at the physical configuration of the quantum machine, and then do you find out like which 3 qubits have that specific like connectivity, and then do you manually assign them, or
if we're talking about my thesis, then no. Yeah, I think that's a very difficult problem, right? Finding a subgraph within a large graph that fits. I think that should be a very difficult problem.
can you just like look at the configuration of each machine and then manually like choose which qubit you want to use?
Yeah, you could do that, but for example, I'm using this as a machine learning algorithm. So in that case, I would have, let's say, 10,000 training samples. So for 10,000 of them, I would need to manually find the correct,
Maybe you can use the like mind embedding, like when you do the.
Yeah, you would need to do that. Yeah. I'm not sure if Qiskit, I think Qiskit provides something similar, right? And no, I mean, finding the optimum mapping from logical qubits to physical qubits, right? Yeah, transformation.
Well, like, is it like do you need to care about that kind of stuff when like doing with if you're doing on a simulator kind of stuff?
No, you don't need to.
So if there's no question, thank you for the presentation. And